Good morning. Give people a couple minutes to join and then get started. All right. Good morning, everyone, and welcome to today's webinar, Centralized Protection and Control, an introduction presented by RLC Engineering. My name is Justin Dodd, and I'll be moderating today's session. Before we get started, I have a few quick housekeeping items. This session has been approved for 1 professional development hour. A PDH certificate will be emailed to everyone who attends the full live session. Please note that PDH credits are only available for live attendees. If you're watching the recording later, we are not able to issue a PDH credit for that viewing. Today's session is being recorded, and we'll send the recording to all registrants within a few days after the event. Please feel free to share it with any colleagues who are not able to join us live today. For questions, please use the Q&A feature in your toolbar. You can submit questions at any time during the presentation, and we'll address them at the end during the Q&A portion. Please don't hesitate to send those in as they come up. Now I'd like to introduce today's presenters. First, we have Ryan Conan. He is a senior protection engineer and team lead here at RLC Engineering. Ryan has over a decade of experience in protection and control design, testing, and commissioning. He focuses on substation systems and leads design efforts for complex utility and developer projects. Joining Ryan is Craig Lakin, principal protection engineer at RLC. Craig has over 15 years of combined experience in protection and controls, generation electrical design, substation design, testing, and commissioning. He is also a licensed professional engineer in several states. And finally, we have Chris Bennett, principal protection engineer and team lead at RLC. Chris brings 15 years of experience in power system design, protection coordination, and control systems. He is a licensed professional engineer across multiple states and has led a wide range of projects, including renewable generation and advanced substation automation. With that, I'll turn it over to Ryan, Craig, and Chris to get us started. Take it away.
Thank you, Justin. So as Justin mentioned, my name is Ryan Conan. I'll be one of the presenters today. On screen, you can see an agenda for today's presentation. So I'll be going first, and I'll be covering the background, history, and industry rollout. Next, I'll turn it over to Craig Lakin, who will review some example CPC solutions. And then finally, Chris Bennett will review the benefit summary and challenges ahead for CPC. So as mentioned, I'll be discussing the background, history, and industry rollout. We'll talk a little bit about P&C, where we're coming from in protection control relaying and where we're going to. So most of us think about, substation protection and control systems. We think about, a dedicated IED that's assigned to an individual, bay, breaker, transformer, or bus, like shown on the graphic on the screen here. CPC will really change that model by moving more of those functions into a centralized computing architecture that will typically be communication-based. IEEE has described CPC as kind of the next generation approach for substation P&C systems. So if we're to give it a definition, And it's kind of a wordy one, but we could say that it's a substation protection, automation, and control architecture where functions that were historically distributed across many individual devices are performed in a centralized or partially centralized platform. So CPC really the approach will eliminate a lot of the relays and devices, both in a traditional or 61850 design, making the system much more streamlined and standardized than a current traditional design would be completed. So this isn't to say that CPC cannot contain any hardwired or traditional electrical circuits, but the main benefit of CPC will be realized by migrating to more of a communication-based scheme that could either utilize IEEE 61850 or a vendor proprietary communications protocol. So CPC is not, contrary to popular, misunderstanding, it's not just one big relay, or it's not simply 61850. It's really an architecture shift that's moving more towards a centralized computing platform. So if we want to compare and contrast CPC with kind of a traditional architecture, again, traditional, architecture, one that we're more familiar with, would have a lot of relays, hardwired CT, PT, as well as status and control points. There's going to be more, copper cabling, more individual device programming. And obviously for all these devices, they need to be housed somewhere, and that's typically within the control enclosure. Obviously that amount of equipment takes up a lot of the space within a control enclosure, and it's typically the biggest driving factor of the size of the control house. So the CPC model consolidates that protection, automation, control, into a central platform that will utilize RIOs and IEDs, and obviously with the reduction in the physical space, right, needed for each of those devices, means a smaller footprint for the control enclosure. So although there could potentially be some more upfront costs for engineering, it's clear to see the benefits for both utilities, developers, or other end users, based, not only on the physical limitations, but also things like simpler lifecycle management, a more integrated type system. So although the idea is obviously very powerful, it has its limitations and challenges, but it didn't appear overnight. So CPC is really the result of decades of change in PNC and substation communications. So to cover a little relaying history, and something we're all pretty familiar here with, in the early 1900s, we saw the introduction of electromechanical relays. These relays, required a lot of physical space, maintenance, and they didn't provide a lot of flexibility. Obviously in their time, they're pretty remarkable devices, but as microprocessors and computing became more prevalent, the limitations became more obvious. So, and then from EMs, we saw a shift over to static state and solid state relays. But as, again, the microprocessor relays emerged, it became very clear the limitations of those original relays. So with phase two, as I'll allude to, these were the multifunction type relays where they could provide not only protection functions and multiple protection functions, but also metering, alarming, and other functions. This was a major shift in the industry because it made engineers more comfortable with a single device being responsible for a variety of functions. And in phase three, we'll see centralized communication-based protection. So although we're calling it phase three, it's really been around just as long as microprocessor-based relays, but for a number of reasons, it was not fully implemented, that we'll discuss here in a second. So why now? Really, the biggest one is that it's the idea was ahead of the infrastructure. So starting with things like processors, right? So processors now are more available, more affordable, more powerful. And then on an industry side, we saw the maturation of digital substation architecture that became not only wider adopted, but the end users became more familiar with such a architecture. Finally, there was finally some pilot projects that proved concept for CPC. So it was one of those kind of standoffs where everybody was kind of waiting for somebody else to trial CPC, to kind of vet maybe some of the deficiencies, some of the hurdles. So once they have been implemented and proved, I think the familiarity and comfortability with them has grown. So as you can see in the graphic here, it shows kind of the iteration of the relays over time. And again, kind of the key takeaway here is that centralized protection has been around, for quite a good amount of time now. It just wasn't implemented. So how is the industry going to roll it out? So obviously, implementing CPC in a brownfield type application presents a lot of challenges, right? So the primary projects that have been chosen for CPC applications are greenfield substations. That's not to say that they couldn't be applied in certain retrofit projects, but it's a better opportunity to do from scratch at this point. Driving the rollout is, the benefits discussed earlier, as well as more that will be covered later in the presentation. But the reduced design complexity, adaptive and integrated protection control should all be, reasons why utilities and developers alike should be thinking more about CPC as a viable solution. The things that are obstacles is some of those that just mentioned, the lack of familiarity for both the folks designing these projects, the operations groups, as well as the testing commissioning for them. So as they become, more adopted, more relevant, a lot of these, should essentially take care of themselves. In the near term, it seems that we'll see increased adoption as there's more standardization, both in design and settings, for these applications. So in talking about standardization, IEEE in 2025, it was approved for IEEE C37300 2024, which is the new guide for centralized protection and control systems within the substation. So although CPC has faced a lot of challenges and there's still clearly a lot of obstacles ahead, it seems abundantly clear that utilities can't keep designing and building stations using the 100-year-old type strategies. It's time to adopt more modern equipment and techniques to meet the needs of their customers. And now I'll turn it over to Craig to cover some example CPC solutions.
Thank you, Ryan. We'll jump right into the first example here. As Ryan kind of alluded to past, like how kind of where we've come from and where we're going. The first slide or example here I have is kind of what I would say is a great stepping stone into the CPC approach. It is not fully a centralized protection communication based. It is what we call a hardwired centralized protection example. In this example, basically, instead of having a bunch of distributed relays, we are now going to have one centralized relay that will perform the same functions as the decentralized relays. So driving right into it, kind of our left example here, the traditional hardwired design would have basically 6 relays in this example, and we'd be consolidating down to 1 relay in the example. All of the functions would still exist. They would just be implemented in software in 1 device instead of in 6 separate devices. To accomplish this, one way you can accomplish this is using SEL's SEL47E relay, and you just use the full capability of the relay. And by doing that, you can basically have line, feeder, transformer, bus, and all kinds of different other functions in that same device as needed. So you're not kind of branching out too far from your kind of tried and true methods or your experience of your teams. You're just kind of leveraging the full capabilities of a device you may already be using in the industry. As I mentioned, it's a great stepping stone. So like, again, if you want to kind of bridge into this space, maybe this is a great example for your first pilot project. consolidating down. Another great feature for this is that difficult situation of the brownfield, as Ryan was alluding to. This could be potentially a great application for a brownfield application, and maybe it's not a full-blown CPC example as I'm showing here in these examples, but it could be such as maybe I want to implement it simply on the feeder protection, and I'm just going to do a centralized protection on just the feeders. And leaving the transformer alone or leaving the line protection alone. So again, a great opportunity for greenfield, good opportunity for brownfield. The key benefits here is obviously you're reducing the relays, and as you can see, we're going from 6 relays on the left to 1 relay on the right. But then I'll note that we have a reduction of 7 relays per system. And I'll explain that a little bit, where in the example on the left, we're already kind of showing utilizing some combined functions in those relays, such as the line relay on the top is performing breaker control functions, and the bus relay is likely performing breaker control functions. That's not fully adopted by most clients or most utilities. So there would typically still be another breaker control relay for the high side breaker and another breaker control relay for the low side breaker. And those breaker control relays would be doing obviously control, so SCADA, synchronizing, tripping. It could be doing breaker failure control if you wanted. So other functions that may be built in here. So really on a typical design, you'd see about a reduction of 7 relays. And the other key to note here is that this is only showing one system, and on most bulk power or bulk electric system design, you're going to have a fully redundant system. And even at the distribution level now, we're seeing a lot more focus on having redundant systems. And that's mostly due to supporting outages. You can take a relay down and not have to transfer customers over to an adjacent substation or transfer it over to adjacent line that maybe can't handle that extra capacity for the short duration. So again, fully redundant systems is definitely the norm now. And so if you say it's a reduction of 7 relays per system, it's really a reduction of 14 relays total. And then we're now talking also about the reduction in the ancillary devices. So that would be all the SCADA functions, the digital fault recording, digital monitoring equipment, phasor measurement units, metering functions, and then also all the like the smaller miscellaneous kind of wiring associated devices, such as like test blocks, fuses, control switches, etc. Lots of reduction in equipment by doing this kind of centralized protection. And all this results in a significant reduction in control and alarm wiring. So as you can see here, basically, we're not changing any of the functionality. We're just wiring the CTs and VTs to a centralized box and programming it with the same functions that the other boxes would have done. So that's a good stepping stone project. Moving on from that, to take it to the next step, would be the going to a communications-based centralized protection system here. And there's kind of 2 ways to accomplish it on the SCL, keeping the Schweitzer ecosystem here. You can do it with their title technology or with their 62850 merging unit technology. And the big benefit with the communication-based approach is you're getting all the same consolidation of relays. You're going from 7, 8 relays to 1 relay. The benefit being that you have the ability to wire your CTs and VTs to merging units out in the transformer or breakers, and then having sampled values come back to your relay, eliminating control wiring and CT and VT wiring to and from your control house to your yard devices, which makes the design much more modular, easier to adapt. It also eliminates some of the hazards and concerns of CT and VT wires between the control house and the yard devices. And one thing I wanted to show here is that while it looks like, well, when the merging unit design, we're adding in all these merging units. So we might be reducing our number of relays, but we're adding in merging units. So isn't that kind of a wash on devices? And I would counter that in saying no, because most devices you're buying, breakers and equipment today, are coming with some sort of discrete I/O device out in them, typically referred to as a RIO or a remote I/O device. And what that is that's just consolidating all the alarms and control points in the device anyways. So all we're simply doing is converting a less powerful RIO unit to a combination RIO slant merging unit. And now we're consolidating all the digitals out in the device and all the analogs out in the device and passing that over the communication network. So by doing that, we're seeing significant reduction in sizing of cables and wiring, and just making the project more streamlined and adaptable for future use. So moving on to the next example we have is ABB's approach to this. So ABB also offers kind of the first tried and true like industry stamped centralized protection device called their SSC 600 device. It is a full-blown centralized protection computing platform. So it's rack mounted. It's not just leveraging on existing relaying technology. It's a standalone new unit. They have their own merging units available, or you can obviously subscribe to any other publishing IEC 650 merging units by other vendors. One of the key benefits to the ABB approach is that their centralized protection can actually run as a software-only solution on other people's hardware. So you don't necessarily have to be locked into one ecosystem. If you find an equivalent processor you want to use, or maybe you want to use two different processors. Maybe you want to use an ABB processor and you want to use somebody else's processor to have some reliability. You can do that theoretically with the ABB approach. And then one of the next benefits that ABB offers, which other vendors as well offer, but I just want to touch on this specific example, is instead of having merging units at each breaker or each transformer, you could have a backup relay out there, such as their REX or REF kind of feeder overcurrent relay. And what that does is it allows you to have the merging unit function, obviously, which will be transposing the signals to a communication base for the centralized protection to perform the actual functions it needs to, but it also can act as backup relays for you. So in this example, in theory, you could have your two CPC devices, and then all these merging units could also be acting as backup relays, which means if the CPC itself goes down, you're not completely out of water on your protection. You still have your backup elements in a more of a traditional approach. So that's another good way to kind of implement a system 1 and system 2 protection scheme. You could go with emerging units and then a backup relay, or you could go with a merging unit and then another merging unit and two relays. It kind of depends on what your kind of cost versus benefit is on your analysis on how you want to implement CPC. Moving on to the next one, and this is the final example that we're going to provide today on how to kind of set this up. Is you can use GE's relays to accomplish this, which is another tried and true industry practice. They kind of lean on their multi-lin family of relays to accomplish it. They also offer a hardwired solution using their GE T60, so you can do the T60 with hardwired CTVTs from many different sources and kind of configure this just like you could configure the hardwired SCL47E. So this could be another great candidate to centralized protection, or if you're very keen on having system 1 and system 2 relays not be the same vendor, that would be a great opportunity to have maybe an SCL47E as your system 1 relay and a GET60 as your system 2 relay, both hardwired as a stepping stone greenfield project, or maybe again, as if you just want to do it on a brownfield and a smaller rollout scale. And then GE also offers a full-blown communication-based centralized protection using their merging units or any other industry subscribing 62050 merging unit. You can jump on that same platform and do that. So that gives you kind of four different examples, two kind of hardwired and two kind of communication-based examples on how you can roll these out. More information can be provided on a one-to-one need basis. Feel free to reach out to us to kind of go through your specific needs. We'll be happy to discuss that with you. So moving on, Chris is going to talk about some of the benefits and drawbacks of CPC implementation.
Great, thanks, Craig. So everybody has heard many of the pluses and minuses throughout the presentation already. So if you want to wake back up and we got to the point of, well, what's in it for me? We're at it. So the basic pros and cons to CPC design come down to what do you need at this very moment. Not every station and situation will benefit from CPC. As Ryan mentioned and Craig mentioned, brownfield might just not be viable for your given budget. Greenfield might just be too complicated based off other factors. So some of the determining factors that you may want to consider is your operating voltage that you're considering it at, your criticality of the station and load stability. You also want to keep in mind, who do you have for installation and troubleshooting? Do you have a team of technicians standing by that are trained for this, or do you have, a company that you like to call in for your testing and troubleshooting support? And then the obvious is the budget aspect of the design. Those are not exhaustive by any means, but definitely some of the higher hand-picked ones. So we heard about the physical space benefits early on, reducing the overall size and number of cabinets, but another benefit that is not immediately obvious is you will have smaller AC and DC loads due to the less devices, and a smaller control house also needs less HVAC units, which can definitely drive up the cost of a project very quickly. If you are running specialized equipment inside the control house for a renewable project, such as a power plant controller or battery storage type controller, they usually have some kind of requirement for what they need for that. So a visual graphic of what we are talking about for CPC is, you see in red that would be a traditional design for something that Craig had mentioned before, with a single incoming line, a transformer, and 3 feeders. We can replace seven of those racks with one centralized protection rack per system, depending on your requirements for system separation and redundancy. You may be able to get away with just the one. Typically, 2 is recommended for redundancy. And what does that look like from the top down inside the control house? Well, what we're talking about here with 2 dedicated racks for CPC, you would have your SCADA HMI telecom racks on the left-hand side in the middle there. Your 2 blue racks now would be your CPC, and we would be eliminating all the racks in red. What that means physically is I can shrink the control house all the way from the right in by a significant margin. Less square footage means less HVAC, less needs, less. I know in Massachusetts recently there was a requirement for facilities above a certain size, so you might be able to dodge some of those. And also, as mentioned there, you do not have as many DC loads to feed. Your battery and battery system can be optimized and reduced. Definitely big cost savings there in the physical realm. Construction, talking about the actual act of putting everything together. As mentioned, every one of those traditional designs needed multiple cables to get the statuses back, the trip signals back, the close signals back, the monitoring signals back, VTs, CTs, power, you name it. That was another cable. So by keeping the cabling local to the device, you're eliminating thousands of copper connections in the cabinets, elimination of 7 cabinets in our example, the miles of cable that you're going to need to run out to the yard. Cable raceway systems are greatly simplified because now I do not have hundreds of cables running from the yard back in. So yard interface boxes may be beneficial. They may not even be required at this point. Conduit and trench will not be as big as in traditional design because we do not have that many cables running back and forth. And just in general, the setup and the construction of this system allows for basically set and drop type construction configurations when the station is being built. I lost my words there. I apologize. The hardwire design, this is what we typically see nowadays in most control enclosures. The racks that we reference are in the picture on the left. At least one, if not two, of those racks per relay zone of protection. On that rack is also many other devices such as switches, fuses, aux relays, handles, you name it. Everything that takes up space costs money, has long lead times in some cases. You see in the picture on the right that those are the thousands of connections that we're talking about. Each one of those little SIS wire jumpers need to be placed, labeled, tested. Takes time, takes money. We estimate each cabinet typically costs about $50,000 just for the equipment and the wiring assembly. And when you factor all that in for who designed it, actually installing it, testing it in the field, ringing everything out, you're looking at probably about $150,000 or more per relay removed from the scheme. So definitely some big benefits there. And to highlight the external cable reduction, we have another infographic of a typical traditional microprocessor wiring scheme for a single cabinet on the left. You can see the many incoming and cross system wiring cables that jump from panel to panel, from system to system, reduced down to a handful of cables on the right on the cabinet. And in this particular instance, you probably would get away with a very small Phoenix style termination block system where it's not worth having entire cabinet worth of termination blocks just for the CPC. So as you can read there, removes most of scale, alarm, and we'll go into safety in a second, but there is a safety component to this as well. So design benefits, on top of what we talked about before, the adaptability is probably the biggest factor here. That we've all been in the situation where I wish I can copy and paste a certain breaker or relay set into my package, and I cannot because each breaker needs something else. It needs something different, something special. In this case, with merging units or even hardwire design, you can keep everything almost exactly the same between different station configurations and still get a massive benefit, and your design time is greatly reduced on paper. As a little bit of an example here, as a mock-up, we have the typical design example that we've been seeing through this presentation on the left. Single line in to a transformer, feeds a low voltage bus out to 3 feeders. What we would see in this design, even with CPC, is you would still have the breaker diagrams for trip coils, closed coils, but because they will have the relay or the merging unit inside of them, a lot of them should be repeat values and repeat sheets, reducing the amount of time and customization for each individual breaker. The tripping and the statuses are all brought back into the centralized protection area to be used as the engineer sees fit. On the right, we can expand that idea with minimal increase in the design sheets, if you want to call it that, If we wish to expand it to a breaker and a half bay, a ring bus bay, and add an additional zone of protection around the transformer, here I have it protecting the bay as well as the transformer. You can also customize it to be just the upper bay as a bus differential. And the transformer differential can be reconfigured to be the high side transformer CT down to the feeders. Almost all the drawings would be exactly the same here. The biggest lift here would be more of the programming and the general arrangement of your software. So definitely some heavy design benefits there, reducing the amount of time and the amount of resources needed for customization. As mentioned before, there's also major safety benefits to CPC. Because we are now reporting exactly what is wrong with each individual device. So traditionally in a transformer, we will gather the major alarms and tripping outputs for use in our protection system. We leave behind a lot of alarms in all devices, such as the first warning signs of loss of oil, loss of temp, loss of you name it. All of these now can be reported and exact problems can be tracked with asset management software. So replacements and failures can be mitigated. On a physical level, we're also keeping high voltage from VTs and CCVT circuits, as well as the high DC current trip circuits, closed circuits, and CT circuits out of the control enclosure. Now, keep in mind that's for full digital substations only. If you opt for a hardwired design, unfortunately, we still will have those inside of the control enclosure, but it is in one central area now and not spread through multiple panels where it might be difficult to locate which wire goes where. Also removes removes uncertainty around wiring point-to-point issues because now we only have one cabinet and everything is communication based. So much easier to check your physical wiring when there is not a whole lot of it. Just to highlight that, typical 3-pole independent operation breaker nameplate on the left there, you will have 5.2 amps of DC current per coil. In this case, you will have over 15 amps of DC current flowing through that circuit back into your control house and back out to the breaker, because that is where the protective relays lie. Not exactly the safest thing. Depends also where your motor charge currents need to run to. If it is a shared system, as sometimes they are, and it does take its feed from the relay cabinet, which in some traditional brownfields can happen. That is not a great safety thing either, but probably another big one that most folks have probably seen on that are on this call that have seen before is the burning up of the CT circuits when there is a massive amount of fault current. Picture on the right there. Definitely not a fun event, and whatever we can do to keep folks safe is definitely number one priority. Just going through some of the programming benefits here versus the microprocessing relays. Everything is in one location now with one setting file. It's much easier to cross-reference and communicate between the different schemes. For instance, fast bus differential, you can instantly detect, because it's the same relay, that my feeders are experiencing a large fault. It's not my bus, so I will hold the bus differential. The data is also freely available. So if you decide in the future that you want to create a new protection scheme based off some status that is coming into the system, it is much easier than trying to communicate that and hardwire or find a way for that signal to become readily available. And as mentioned before, we're reducing the amount of SCADA DME equipment. And one of the last benefits here is it is greatly, it becomes much easier to manage your firmware CVEs, the critical vulnerabilities and exploitations. As SEL and other vendors publish issues that happen with cybersecurity events, having one device versus 7, as Craig had said, is a lot easier to maintain firmware versions. A little bit on the challenges side now. These are the things that are major drawbacks. 61850, IEC 61850 is typically not new user friendly. If done correctly, there is ways to cheat the system a little bit, but your tags and your data streams can be very messy and create hazards for folks in the future if you're not careful from the get-go. So there's typically a barrier to entry there. Some of the vendor solutions, as Craig had mentioned, SEL, ABB, GE, if you take their internal approach, they may have different requirements for setup and communication and power versus each other. They also may use a completely different protocol as well and may not be friendly to talk with each other. And ultimately, you're at the vendor's mercy for whatever it is that you're trying to do. As an example here, just taking from the cut sheets, on the left, I took the SEL TMU, which is the merging unit that would sit out at the device. And in the specification, it allows for 4 SFP ports. SFP is small form factor pluggable. It means that you can effectively use fiber or Ethernet, copper Ethernet cables if you so desire, depending on your need and network and system. That's to get the communication back to centralized device. The ABB Rec 600, for instance, for the merging unit, it will only provide you 3 RJ45 base T100. Now that means that it is a fixed copper wiring solution that it's expecting for Ethernet cable. The issue here is that we may have interference, we may have a distance problem, we may need a separate fiber converter. So depending on your application, some vendors might be better than others. You may be stuck with a vendor, like Craig was mentioning, ABB is a little bit more flexible with their relay and the backup, but you also may have a physical limitation on the actual design side. So some of the challenges to be aware of. Walking into that a little bit more, adoption challenges, the inability to commit fully to an all-digital substation. It is a very scary thing in our protection and control world to give up what we've had for over 100 years now. Having CTs and copper cable running where we know what is the voltage drop, what is my current output going to be, and trusting that a digital network is going to stay up, at all times is not easy. But as Ryan mentioned, we've already had that evolution once, and now we're walking into another evolution now. The unfortunate part is that the hybrid design is the worst of both worlds. You're still running all your cables, you're experiencing the losses with copper, but you also need to set up the data mapping and the relays the same way as you would for a fully digital 61850 station. So you're using more time, more resources, which makes it somewhat not beneficial depending on your specific need. As mentioned before too, we also have issues with outages or maintenance. If one of the relay systems dies or is failed or needs to come out for maintenance, what would we do with just one relay that literally controls the whole station? To combat this, you may have to design a third standby system based off either laying on system 1 or system 2 or system A, B, primary backup, or design it as a completely separate third system. Z windings or off breakers or breaker CTs, I should say. But again, all comes down to cost. And I think one of the bigger issues is also scalability. So far, every example that we've shown you today has been for a smaller station, 3 feeders, 1 transformer. As we walk into larger stations that have multiple transformers, multiple bays, multiple buses, we can have issues from simply just not enough current inputs to do what we want, all the way to complete traffic jams behind the network switches because there is way too much data flowing on our network OT system, operational technology versus IT. So to highlight that a little bit, if it wasn't obvious earlier in the design, the SEL 487E, for example, as of right now, has a limitation of 18 total current inputs for 3-phase inputs using one for each phase. That leaves you 6 input devices. That may work for a small station. If you have a larger station that has more than 3-4 feeders, depending on the configuration, it might require a design overhaul on the right-hand side. There's an interesting overlap on the right-hand side that SEL had presented, but that does create complexity and repeatability becomes a sacrifice. And finally, the engineering challenges that come along with 61850 and these all-digital centralized protection control designs is that it will require more upfront engineering for data mapping. You need to set up your Goose MMS subscriber network, and even with SEL, you do need to make sure that you are connecting the data streams correctly. I will use data streams as a generalized term. Also on top of this, as I was just talking about, is the PNC engineers and the design engineers will likely need some kind of networking experience to account for all these changes with fibers and SFP ports and Ethernet ports and Ethernet switches and what's best for my design. Traditionally, those are 2 completely separate worlds, and now they're being merged together, which could create some challenges as to what's compatible, what's best, what speeds do I need, bandwidth. It becomes a challenge for roping in more folks than ever before. And finally, one of the not so obvious downsides is that fibers and fiber installation is usually finicky and difficult. Depending on your available vendor, what types of fibers you want, and what equipment you're using, it can be long lead and it can be difficult to install and procure. So, yeah, those are some of the highlights to the challenges. If you do have any other questions about the challenges or how we can get around some of them, RLC and myself, Craig and Ryan can definitely assist with that if you reach out. So I'll hand it back off to Justin for some Q&A.
Awesome. Thank you, guys. Yeah, we had a few questions come in along the presentation. And again, if any others come up, please feel free to put them in the Q&A. If we're not able to get through all the questions in the remaining time, we'll send those out with the presentation recording afterwards. So first one to the team, what happens if the fiber is cut or lost with a fully digital implementation?
Right. So that's obviously the trust of the fully digital. If the fiber is cut, we would be running 2 separate paths for the fiber, ideally, so that way the second system of CPC would be able to continue on while you are able to troubleshoot. Depending on the fiber failure, a full cut would mean somebody has been doing work at the station and did not follow the instructions correctly. But if the fiber does shatter or break or become clouded, the hope would be that you run a separate fiber for backup reasons to quickly swap over and get the system back up and running.
Right. Can metering functions be put into CPC as well?
I guess I'll touch on that one. So the short answer is, in most cases, it depends on, metering is kind of a catch-all word. Metering can often mean like SCADA metering, check metering, like relay metering. It can operational metering. It can also mean like revenue grade metering. I would say that like the operational check metering, SCADA metering, regional operator or ISO operator metering, that definitely can be put into an SC or a relay device over CPC. The revenue grade metering, we historically have always seen that kept separate. It's just different departments, different needs, different equipment. So that typically is not put into the centralized protection.
Okay. How does CPC affect or impact scheduled outages and maintenance?
That's another great question. The outages and maintenance traditionally will be run by the operations group, and they will go through a list of affected devices. But in this particular case, because we do not have a relay per device, they will need to be trained on what exactly is in service at any given time during an outage or a maintenance event. So traditionally, you have a line, you need to take it out of service. The biggest problem that we've traditionally seen is that, okay, we're going to take all the line relays out of service as well, just in case something happens. In this case, the CPC would be labeled as the line device, and if you take that out, the rest of the station is going to go with it. In this case, it would require some extra training and some additional potential software controls through SCADA to say, hey, the line protection needs to be altered into a different state. So you may have different protection groups depending on what kind of maintenance and outages you expect for your given station, or you might have special schemes that enable or disable certain elements based off what is being taken out of service. So definitely some challenges that need to be worked through as a whole for operational and maintenance safety, but easily surmountable with proper communication and support from your local ops ops folks.
All right. Is there anything to watch out for with devices in or near the yard equipment?
That's an interesting one. We have seen instances of merging units and relays within the enclosures in the yard that they experience large temperature swings. A lot of these relays are rated for some plus minus large degree Fahrenheit, but you can imagine in the midst of summer, outside temps hit 100 degrees Fahrenheit in the Northeast. It's fairly humid. Cabinet can easily be 80% humidity with 130 degrees Fahrenheit inside. And the devices start acting a little weird. So there are considerations here to be made for how exactly do you put those devices in the yard. There's definitely talks about the ratings of the device. There is talks about ventilation, and normally we see some kind of minimal resistor to burn up extra humidity, but there's also talk of some kind of AC HVAC kind of system, if it was even possible. So there definitely needs to be some kind of expansion there, but it's not insurmountable. It's just one of those things that we've never really had to worry about, since most mech cabinets have, by and large, not had any kind of IED in them. So.
Right.
Well, I guess I'll add to that, Chris, that in the last, I'd say, decade or two, we have seen a lot more percolation of IEDs into control cabinets in the yards with the Rio devices and like LTC controllers, those sorts of things are being more electronic devices are getting installed in control cabinets, and we haven't seen them failing like every day. Like they do fail occasionally, but for the most part, they are hardened devices with the right specifications to make sure that they can survive those environmental conditions.
Right, exactly. And issues can prevail depending on what the device exactly is, but depending on where you're installing it, if you're installing the device in Arizona, definitely would look for higher heat resistance, or potentially a NEMA rated box that you could still get your dust proof certification while also providing some sort of ventilation. Those are the types of challenges, depending on your location, that may come into consideration that, yeah, for any type of yard equipment.
Great. Do you see any use or benefits of AI for CPC designs?
AI. That's a good one. Definitely for CPC, there is a lot of data to be held and processed by one unit, and we as humans tend to lose track of, data points and mapping and other information within the system, unless if it becomes relevant. So, for instance, if we're gathering 20 points per piece of equipment at a minimum, you're looking at 6 pieces of major equipment. That's 120 data points right there. You do any processing on those, it could quickly explode into some kind of large mess with too many things floating around. AI could help you keep track of that. And also with the 61850 data mapping, you may be able to get an AI agent to help you create those data streams and Goose MMS subscriber accounts to keep things tidy and straight on your network versus trying to manually configure and do that yourself. Definitely an area that can be researched and looked into, but so far AI has been fairly niche and will probably require some serious training on what is desired first, but definitely an interesting use case.
All right. There's another one you have to break out your crystal ball for. Why, with so much evolution in the protection space, what do you think comes after CPC?
Hmm. For me, my guess, honestly, with CPC, I think the next iteration is multiple station CPC. So instead of having one central device per station, we would be setting up a central server within a building, a utility headquarters, or just any central location, and we would be providing protection and control from that central area out to each substation. So, relay maintenance would by and large go away. The control houses would just be, internet backbones or, dark fiber backbones. That's probably where the system is going, and who knows, maybe even AI is the one that's watching for current spikes and knows exactly how to reconfigure the system for system stability. That's probably where we're going. I mean, we started with 3 relays for one function, and we got down to 1 relay for many functions, 1 relay for many devices. So why not 1 device for many stations? It's probably what's next, right?
I think another big change coming to the industry, which kind of plays into the CPC design, is the changing of the sensor instrumentation. So there's already a lot of push for low energy CTs and VTs. So instead of traditional hardwired or hard wound copper CTs or copper capacitive transformers, we would see low energy, either optical or other means of measuring current and measuring voltage. So that signal is already going to be digital coming out of that device. So we're going to need a digital substation to handle that digital value. So that's another reason for CPC, is that the instrumentation is going to be changing in the next probably 20 years as cost becomes more lucrative.
All right. Why is networking knowledge during the design so important for CPC design?
Yeah, this one's the tough one. Networking knowledge is definitely required, not only for the interoperability, like I showed before with the fiber, the Ethernet, but also depending on the size and the amount of data flying around, the network switches can actually get overloaded due to the amount of data flying around. And the last thing that you need for CPC is that the data flow stops, meaning that I don't have the most up-to-date CT analog value, so now my differential doesn't work right, or my VT is off and I haven't gotten a fresh reading in a while. It we cannot have the network backbone fail on us while we're trying to provide protection. So being able to optimize and manage that correctly for speed and bandwidth is going to be a new critical component in this design. So getting it correct early on and trying to future-proof the station is probably well worth it versus trying to get it to barely work at all in the beginning and then have trouble later on.
All right. Thank you, Chris. Well, we're coming up on time, so we'll cut it there for questions. Truly appreciate everyone taking time out of their day to attend the presentation. I hope you were able to get something new and valuable out of it for knowledge. And we'll follow up with the recording of this session and PDHs in the coming days. Thank you once again, and look forward to seeing you on the next webinar. Thanks, everyone.
Thank you all. Have a good one.
Thank you, guys.